Thank you, and good evening a second time. So the first talk was about basically how the universe is put together, and the second talk is how we know that. In other words, the telescopes that tell us what's going on, that allow us to observe the universe. So telescopes, of course, have been around for some 400 years or so. Galileo wasn't necessarily the first, but he was one of the first to document what he saw when he turned a telescope on the sky. Since then, telescopes have been changing, and over 400 years, they've changed almost beyond all recognition. We now have larger telescopes with, rather than lenses, a few centimeters in size. We now have telescopes that use mirrors. That's the preferred way of collecting light rather than using lenses. And these mirrors have grown from a few meters to many meters in size. Some telescopes are above the Earth's atmosphere. Perhaps you already recognize the Hubble Space Telescope and the James Webb Space Telescope. I'll be saying a little bit more about those shortly. But also, telescopes here on the surface of the Earth, on the tops of various mountains, are being built with ever larger mirrors because we always want to collect more light. Essentially, if we want to see faint objects, we need to collect as much light as possible. That's why there's always been a drive to make larger and larger telescopes. And coming online in a few years is this monster telescope. You probably can't see, but there's a tiny little dot at the front. That's a standard person. Okay, that's 2 meters. So these are going to be absolutely huge. We can get a rough idea of the scale by this rather complicated looking graphic, which gives us simply a number of different telescope mirrors to scale so that we can judge just how big they've become. Galileo's telescope is way too small to be on this. Even the smallest mirror or lens up in the top left is 1 meter in diameter. And for those struggling to get the scale of these various telescopes, either there's a standard human in the bottom right, or perhaps more useful, an edge of a tennis court or a basketball court, to give you an idea of the sense of scale. The largest telescope in the world at the moment is Gran Telescopio Canarias. That's indicated by this pattern at the top in yellow. Notice that these very large mirrors are not made with one piece of glass or one piece of metal. They're made as small segments, which are then put together to act as if they were one large mirror. That's simply easier to manufacture that way. The size of this telescope at the top there is approximately 10 meters in diameter. They're hexagonal, so we can't really talk about diameter, but you know what I mean. Roughly the size of a circle of 10 meters diameter. In other words, a little bit larger than the model of Gaia that's sitting behind me at the moment. Notice there are plenty of telescopes that are smaller, generally older, and there are big mirrors coming online, as you can see from these two on the right-hand side. Ultimately, they are going to be 30 meters or 40 meters in diameter. Not so much the size of Gaia, more the size of this building. Space telescopes are somewhat different. You can see a few of them in the bottom left-hand corner, the Hubble in the bottom right of the red rectangle and the James Webb in the bottom left of the red rectangle. You can see that regardless of the fact they're quite large for what they are dwarfed by the Earth-based telescopes, and that's simply a reminder that it's very difficult to put telescopes in space. It's very difficult to put a large telescope on the top of a rocket and send it up into space. Therefore, space telescopes have always been on the small side. But they're still worth putting up there because you get above the blurring effect of the Earth's atmosphere, and hence you can probably see more detail with a small telescope than you can with a large telescope sitting on the surface of the Earth, even one sitting on a mountain top to try and get you as high as possible above the Earth's atmosphere. So decades of development have taken us from telescopes with centimeter-sized lenses or mirrors up to meter-sized, and you can see we're going towards tens of meters before too long. There can be few people who don't recognize the Hubble Space Telescope. I would argue that even people not in the least bit interested in science or astronomy would probably still recognize this for the amount of work it's done in the last 30 plus years. Remember, it was launched in 1990, 34-ish years ago. So it's getting to be a real old trooper now. It's been up there for a third of a century. And one of the first things it did was try to get an idea of how big the universe is and what's out there by deliberately pointing to a patch of sky where they thought there was nothing there. They basically have already mapped out quite a lot of stars and quite a lot of galaxies. They pointed the Hubble Space Telescope at a patch of sky where they thought there was nothing, and then basically took the longest exposure they could get away with. This is an exposure of approximately 10 days. It's like taking a camera, exposing the lens, waiting 10 days, and then closing the lens again. Not quite like that, but effectively. There are a couple of stars in our own galaxy that show up in this image. There's one here, and there's one there, and every other smudge you can see is a galaxy, not an individual star. So in other words, we've got thousands of galaxies by taking a long exposure of nothing in particular. So we deduce that if that's typical, in other words, if there's no particular reason why we would expect to get more galaxies in this direction than any other direction, we can simply say, with the field of view that we know the Hubble has, if we capture 5 or 6 or 7,000 galaxies, whatever it happens to be, then we can deduce how many there must be in the entire universe. So the Hubble Space Telescope, one of its iconic features is the fact that it basically told us how big the universe is. It tells us that the universe is full of something like 1 trillion galaxies, at least hundreds of billions of galaxies within our observable universe. It gives us a sense of scale. The actual chunk of sky that the Hubble can see is actually quite small. If we think of the full moon can be covered by your little finger at arm's length. You tend to think of the moon perhaps as being rather large in the sky, especially around full moon. Next time there's a full moon, just hold out your hand, you'll realize that you can cover it with your little fingernail. The field of view of the Hubble Space Telescope, compared to the size of the moon as seen from Earth, is tiny. The Hubble can only see a tiny patch of sky. That's why when it's observed thousands of galaxies in that field of view, we deduce that we can scale up to perhaps 1 trillion over the whole sky. Just to make sure it wasn't a fluke, it took another picture a few years later. And if it took a picture over there and found thousands of galaxies, a few years later it took a picture over there looking in a completely different direction, and it took a similar field of view, similar exposure, and again it got thousands of galaxies. Again, there might be 1 or 2 stars within our own galaxy in that field of view, but pretty much everything you can see is a more distant galaxy. Some of them appear to be quite large, so they might be quite close. Some of the galaxies are tiny points of light, and they are probably very distant galaxies. But that tells us that the universe looks pretty much the same in all directions. We're not in any privileged position. We are sitting in a place where the universe looks the same regardless of which way we look. If we look at galaxies that are closer to us, with the same sort of resolution as something like the Hubble Space Telescope has, instead of looking at very distant galaxies, if we look at a galaxy that we know is relatively close to us, then we get an enormous amount of detail. And that allows telescopes, some Earth-based, some space-based, to look in detail at, right, what stars are glowing in these spiral arms, what's happening in these star-forming regions, these little bits of pink, etc. With this much detail, if we take images of not just one, but many thousands of galaxies, we can start to build up an understanding of how galaxies are the way they are. That, in tandem with the sort of simulations that I was showing you in the previous talk, in which we use simulations to try and understand the structures that we see with these sorts of observations. Again, as I mentioned before, not all galaxies are in isolation. It appears that a lot of galaxies are interacting with neighbors. This one perhaps ought to be a nice spiral structure, but it appears to be distorted by the presence of this galaxy at the bottom. Its gravity of one is affecting the stars in the other, so neither galaxy looks as well formed as you would expect if it was entirely isolated from all of its neighbors. And the more galaxies we look at, the more galaxies we observe, the more common it is to realize that galaxies interact with their neighbors. It's not a 1 in a million thing. It's a many, many galaxies will interact with their neighbors, part of the evolution of galaxies. Here we see it in its most sort of apocalyptic form, this is actually two galaxies in the process of colliding with each other. Roughly speaking, that's one galaxy on the right and one galaxy on the left. We deduce that these galaxies have spent quite a while getting closer and closer, and now they are actually crashing into each other. Not quite as bad as it sounds, because when two galaxies crash, because space is so big, the space between stars is so big compared to the size of a star, when two galaxies crash into each other, the stars themselves probably don't hit each other. So the galaxies pass through each other without any stars actually colliding with other stars in the other galaxy. But in the process of one galaxy going through the other, notice how much pink there is. Remember, pink is clouds of hydrogen which are probably forming new stars. Look how much pink there is in the region where they're colliding. Two galaxies colliding will produce a riot of new star formation. So far from galaxy collisions being the end of a galaxy's life, in many cases it signifies the rebirth of a galaxy, because many new stars will be born as a result. I said last time that when a star comes to the end of its life, it might slough off its outer layers, and those outer layers would form a nebula, a big cloud in between the stars. This is the fate of our own sun. This is a planetary nebula called the Helix Nebula. It's visible low down in the south during the summer, not this time of year, in the constellation of Aquarius. And again, telescopes with large mirrors that are able to look with high detail, high resolution, allow us to have a look at this and deduce something about the star that must have existed before this particular nebula was formed. The star right at the center there is the little white dwarf that's left over once the rest of the star has been thrown off into the interstellar medium. So roughly speaking, this is what our sun will look like in a few billion years' time, as seen from quite a substantial distance. If the star is massive enough, it could end like this. This is a supernova remnant. It's called the Crab Nebula. This star, which we now can't see, it's in there somewhere, a star blew itself to pieces. As seen from Earth, it happened in 1054, because there are records on Earth. The Chinese recorded that in 1054, a very bright star suddenly appeared in the night sky. And when we work out where they said this star appeared, that is what we now see. So 1,000 years later, the star, after exploding, has now produced all of this material, which is slowly expanding outwards. I'm not going to show it here, but pictures taken years apart show that this nebula is indeed still expanding. It's 1,000 years old, but if you take a picture 10 years apart, then it will have grown by approximately 1% of 1,000 years. So we can actually see, to some extent, things changing in the sky, even though they change rather slowly. Nebulae can look absolutely spectacular. This is part of a star system called Eta Carina. It's in the southern hemisphere. We can't see it, unfortunately, from the United Kingdom, but the Hubble Space Telescope can point pretty much anywhere it likes, and so it took a picture in the center of this nebula. It produces wonderful images and wonderful detail. The colors are not the colors that you would see if you look through a telescope at these objects, because the Hubble Space Telescope and most other telescopes are trying to show you what is interesting, not necessarily this is the true color of this object. In other words, the colors that make up an object like this are decided by the people filtering the light, so that the red represents a particular element. The red represents where is the sulfur emitting its light. The green represents where is the hydrogen emitting its light. The blue is where is the oxygen content of this nebula emitting its light. In other words, the colors tell you not simply what it looks like, the colors tell you what is it actually made of. Scientifically, that's much more relevant than simply can we make a nice pretty picture. So for most images produced by the Hubble Space Telescope and others, they make no particular attempt to make it look like it would look with your naked eye. They do it for scientific reasons, to show what it's made of. Perhaps a more common one that you might have seen is the Pillars of Creation. This is in a nebula that's easily visible from the northern hemisphere in the Eagle Nebula, and this was a picture taken early on in the Hubble's life and then re-imaged when its cameras got replaced and upgraded years later. So this is now quite a common image shown many times since it was originally taken back in the 1990s. This is a star-forming region, so we have a lot of hydrogen gas, possibly a few other elements mixed in as well, but mainly hydrogen gas. And what they think is happening is that buried within these various gas pillars, there are stars being born. The hydrogen clouds are collapsing, stars are being made, and those stars are just about turning on, just about starting to produce radiation. And the radiation from these very young stars is, if you like, sculpting the gas around them, because the radiation is sent off in particular directions as the star forms, and it starts to hollow out particular areas and sculpt the gas, which might be under gravity wanting to form just by collapse, but because the stars are pushing outwards because of their radiation, they start to produce some very interesting structures. But one of the problems is we can't really see what's going on inside these regions. These regions are so dense, they're nowhere near as dense as, for instance, the air in this room, but on a galactic scale, there's a lot of material there, enough material to stop us seeing what the stars are doing inside these gas columns. So we can't see the stars forming. We need a different way of imaging. We need a different telescope to look at these objects, ideally to look inside these objects, which is why the Hubble Space Telescope is not the ultimate space telescope. Others have been built to take us beyond what the Hubble can see. And one of those telescopes is the James Webb Space Telescope, launched 2 years ago on Christmas Day 2021. The James Webb Space Telescope works in the infrared part of the spectrum, and infrared, if you like, penetrates these rather dusty regions where we can't see stars forming, and we can't see if planets are forming around these stars. But by working in the infrared part of the spectrum, which is what the James Webb Space Telescope was designed for, we hope to be able to see more of these early formations of stars and early formation of planets around stars. The James Webb Space Telescope has a much larger mirror. Instead of the 2.5 meters of the Hubble mirror, the James Webb mirror is some 6.5 meters in diameter, and as you can see, it's made from hexagonal segments. The basic reason for doing that is not only is it easier to make a mirror that size, but also it had to be folded up in order to get it on top of a rocket. So basically it was tested on Earth for many, many, many years, and then they folded it up like a piece of 3D origami and stuck it on the top of a rocket and launched it in the hope that it would unfold correctly and end up with the telescope that they wanted. Unlike the Hubble Space Telescope, the James Webb is not in orbit around the Earth. The Hubble is circling overhead a few hundred kilometers above our heads, but the James Webb Space Telescope was sent to a particular parking spot. These red dots here indicated relative to the moon going around the Earth and the Earth going around the sun. These 5 red dots are parking places. They are places that you can put a spacecraft and it will stay there. So they're very convenient parking spots if you wanted to put a telescope somewhere other than in orbit around the Earth. And the James Webb has been parked around this particular red dot called L2. That red dot is basically hovering about 1 million miles away from the Earth, and it's sitting directly above midnight. Remember, midnight is the point directly opposite the sun. The sun-facing side of the Earth, that's noon, and the midnight is the other side of the Earth facing away from the sun. So that point is midnight, that point is 1 million miles above midnight. That's essentially where the James Webb Space Telescope is hovering. Why don't you put it in orbit around the Earth? We want to keep the James Webb as far away from the Earth as is feasible, because the Earth is a source of heat, and if the James Webb Space Telescope works in the infrared, it would be swamped by the heat of the Earth or the heat of the moon, certainly the heat of the sun. So it's parked over here with a heat shield which keeps all of that heat out of its field of view. What is the James Webb Space Telescope going to be doing now that it's up there? One of the things I mentioned before, it's going to be looking at the early forms of star formation, looking to see how stars are born in the very dusty environments like the pillars of creation, and it will be looking at how planets are born. Can we understand how solar systems come to be? But another of its main tasks will be to look back in time as far as possible. Remember, the speed of light is a finite thing. Light travels fast, but at a finite speed. The length of time it takes light to get from the moon to here is about a second. So we're seeing the moon, whenever you see the moon in the sky, you're seeing it as it was 1 second ago. When you're outside and you feel the warmth of the sun on your face or the back of your hand, it's taken 8 minutes for the light to get from the sun to the earth. So if you ever to look in the sky, don't look at the sun, but basically the sun is as it was 8 minutes ago. When you look at the Andromeda galaxy, it's taken 2.5 million years for the light to get here. So you're looking at the Andromeda galaxy as it was 2.5 million years ago. How far back in time can you actually go? If the Big Bang was here, kaboom, and we are now 13.8 billion years after the Big Bang, then if you look at more and more remote objects, you're looking further and further and further back in time. So how far back from now can you go by looking at more and more distant objects? Well, you can go quite a few billion years into the past. We think all the interesting stuff in terms of star formation happened in the very early universe, not in the last few billion years. So our sun has switched on and become a star in the last few billion years. But we can ask ourselves, when were the first stars? When were the first galaxies born? We think it was sometime in that region within the first 1 billion years. And if we really want to understand why the universe is the way it is at the moment, we really need, ideally, to get back and look at, right, what did the first stars look like? What did the first galaxies look like? Can we get back to this time period here? If we expand it out so we can see it a little more clearly, so this is a fraction of a billion years, so there's the Big Bang, and this is hundreds of millions of years after the Big Bang. The Hubble Space Telescope has been looking back as far as it can for many, many years now, and it's got back to about here. It's looked back to about 500 million years after the Big Bang, and what does it see? It sees galaxies that already exist. It sees stars that already exist, implying that stars must have been born before the first 500 million years. It is hoped that when the James Webb continues its observations, continues to look for the most distant objects it can, maybe it'll get to the point where it finds, well, if we go back that far in time, we can't see any galaxies that are formed the way we understand them. Maybe it'll see something else. Maybe it'll see black holes in the process of formation before we see galaxies in the process of formation. So it'd be nice to think that ultimately the James Webb Space Telescope will take us back to the very, very early universe, to the point where surely stars must be starting to form. We haven't got there yet. The James Webb Space Telescope has got about as far as the Hubble. It's still exploring this region, trying to push it as far as possible towards the first 100 or 200 million years. And it'll be interesting in the next few years to find what the James Webb Space Telescope tells us about how those early stars formed and exactly when those early stars formed. So after the James Webb Space Telescope unfolded, which it did successfully, much to the relief of the people who built it, it started sending back images of planetary nebula, images of galaxies, images of nebulae, and it started taking data from some planets that are going around other stars. We have now deduced that there are planets going around other stars which have atmospheres in which there is water, in which there are other chemicals which we can see because we can identify which particular wavelengths of infrared light are absorbed by those atmospheres. And by looking at, for instance, star formation, here a very bright star is, if you like, excavating, because of the radiation from this star, it's excavating a cave in the nebula in which it was born. And by looking at different wavelengths, so if we zoom into a particular region, the James Webb is able to say, right, we'll assign the blue color to this particular wavelength, which tells us what the hydrogen is doing in the neighborhood of this star. And we'll look at a different wavelength, which we'll label green, which tells us what hydrogen is doing when two hydrogens come together to make a molecule of hydrogen. And at a different wavelength, which we'll label with red, will show us what the dust is doing in this environment. So we're able to look at how this star is forming and what is the gas doing around this star. What's the hydrogen doing? What is the atomic hydrogen, the molecular hydrogen? That makes a difference because hydrogen on its own or hydrogen in a molecule will affect the way stars are being born. And it also will affect how much dust there is in the region around a star-forming region. The dust will probably end up collecting into planets at some point. So by looking at different wavelengths of infrared radiation and assigning them different colors, we can start to understand early planet formation as well as early star formation. Remember the pillars of creation? The James Webb Space Telescope revisited the same structure, but now it appears to be much more diaphanous. Notice that we can actually see a lot of the stars through the pillars of creation because we can now start to see inside what's going on, whereas we couldn't. There's still some regions which are a little bit too dense, but now we have a much better chance of seeing what's going on inside to give us an idea of what these early stars are doing. This is just an indication that James Webb Space Telescope doesn't see the same thing as Hubble. That's James Webb, that's Hubble, the same galaxy imaged with both telescopes. Notice that the James Webb shows something very bright in the center, which apparently the Hubble doesn't. So maybe that's a supermassive black hole, which for whatever reason is obscured in the Hubble image because it's just too much dust there for the Hubble to see what's going on. But the James Webb Space Telescope can see through the dust and shows us that there's something very bright at the heart of this galaxy. Many more images like that are required for us to fully understand what's going on in these sorts of images. But this is a reminder that the James Webb is not a replacement for the Hubble Space Telescope. They are going to work in tandem for many years to come. This is an early star formation. We think a star is being born right in the center here, and material is funneling down from the nebula, and the early protostar, the star that's just being born, is producing a lot of light, which is lighting up at the top and the bottom the infalling matter. So again, we're getting early information about star formation. Let me finish in the last few minutes by telling you about another telescope that's coming online. It's got the horrible title of the Large Synoptic Survey Telescope. It's now been renamed the Chamonix Telescope, but the LSST acronym has been around for quite a few years. So even though the telescope isn't called that anymore, they decided to say, well, let's survey the sky and let's call it the Legacy Survey of Space and Time. That way we can keep the acronym. And the web page stays lsst.org, so we don't need to change the web pages either. What they mean by a survey of space in time is that this telescope is going to sit on the surface of the Earth and is going to map large chunks of the sky, and it's going to map out everything it can see over and over and over again. That's why it's a legacy survey of space and time. It's not just what's in space, because it's going to be revisiting objects day after day, week after week, month after month, year after year. It's going to show us how things are changing over time, as well as what they look like now. Remember, I said that the Hubble Space Telescope only sees a very small field of view. You can't survey the entire sky with the Hubble Space Telescope. It's got such a tiny field of view, it would take centuries for it to map out everything in the sky. The intention is that the Large Synoptic Survey Telescope will map out everything it can see in the sky in 3 nights, not 3 centuries. It'll do that partly because it's got a huge field of view, much bigger than that red rectangle. So big I couldn't actually get it on the slide. Imagine that circle being complete. That's the field of view of this survey telescope. How do you make a telescope with such a large field of view? Well, you start with a large mirror. Okay, that's not an icing cake. That is a mirror before they've ground it to the right shape and covered it in metal to make it reflective. But you can see the size of it. It's an 8-meter diameter mirror, roughly the size of Gaia behind us here. So you start with a large piece of glass which collects a large amount of light. But of course, if you want to photograph or image a large chunk of sky, not only do you need to collect the light, you need a large camera. Now, just to give you a sort of sense of scale, no, that's not it. That's just for an idea that the camera in your phone, of course, is only a few millimeters in size. It has to be only a few millimeters to fit it in the phone. The scale of the chip in the Hubble Space Telescope camera on the same scale is approximately shown by that blue square there. In other words, it's about 4 centimeters by 4 centimeters. It's not necessarily that much bigger than the chip that you might have in your camera. If you've got a digital SLR camera, you probably have a chip in that camera that's not much smaller than the chip in the Hubble Space Telescope. It's a 16 megapixel chip, so 16 million pixels in one chip, 40 millimeters on a side. If you want the Large Synoptic Survey Telescope to record a large chunk of sky, you need a bigger chip. So what they did was effectively say, well, we know that we can cram 16 million pixels into 4 by 4 centimeters. Let's take a chip like that and add another 8 of the same to make a sort of block. And let's take that block of 9 chips and add another 8, and then add another 12, and then add a few more to make sure that we're pointing in the right direction and we've got everything focused. Now, it's difficult to judge just how big that is compared to the Hubble chip. So for the people in the live audience, I've made a one-to-one mock-up of the chip that's in the Large Synoptic Survey Telescope. That is the size of the detector compared to the one in the Hubble Space Telescope. It is absolutely enormous. If that's the size of the chip, you can imagine the size of the camera, and you can imagine the size of the telescope in which that camera has to sit. So this particular telescope, coming online in a few years, will produce enormous images, 3 billion pixels per image. It'll take an image every 15 seconds, and every image it produces will have 3 billion pixels in it. Now, I can't possibly show you what those images are going to look like. I can't even show you a simulated image of what they're going to look like, because neither my laptop nor this projector can show you 3 billion pixels. So just to give you an idea, imagine that tiny black square there, which is a tiny fraction of the whole image. What might you see when you take a 15-second picture of the sky? Well, you might get something like that. You might get thousands of stars, hundreds of galaxies, maybe the odd supernova or two, probably a few asteroids. And that is only 0.03% of the entire image. The real image you get in 15 seconds will be 3,000 times bigger than what you're looking at on the screen. And it will take a picture every 15 seconds, all night, every night, for 10 years. So the amount of data coming out of this telescope is going to be vast. It's going to be able to catalog billions of stars in our galaxy. It's going to be able to catalog billions of galaxies in the universe. It's going to be the biggest survey of its type ever conducted, and it will take about 10 years to do the survey. It's going to look at a large chunk of the stars in the Milky Way. Not all of them. Some stars in the Milky Way are going to be very difficult to see because they're on the other side of the center of the galaxy, because we're here and it's difficult to see stars on the other side. But it will be able to map out the positions and colors and movements of various stars in the Milky Way, as well as the same for various galaxies. Maybe, we hope, it will also tell us a little bit about this enigmatic dark matter that's out there. We know it's out there, but we can't see it. This, of course, is just an artist's impression. Is dark matter spread evenly across the universe? Is it spread evenly across the galaxy? Is it spread evenly across the solar system? Is it clumped? We don't know, but maybe the Large Synoptic Survey Telescope, when it surveys lots of stars and lots of galaxies via a mechanism I'm not going to describe in detail, it might be able to start to piece together the jigsaw that tells us where dark matter is in the universe, even though we can't see it directly. And then we've got these monsters coming online. Again, look at the foreground, there's a couple of people standing next to each other, and there's a couple of people standing on the gantry next to the telescope. The telescope mirror will be some 40 meters in diameter. It's being built now. It's going to be ready in a few years. What do you call really big telescopes? That one goes under the ludicrous name of the European Extremely Large Telescope, built by Europeans, fine, but extremely large telescope? Well, you can see that that's this green one here on the right-hand side. Is it the biggest one you can conceive of? Well, it's certainly the biggest one we can afford at the moment in terms of the taxpayer footing the bill. But people have thought, well, wouldn't it be useful to have an even bigger telescope than that? Remember, light is everything. The more light you collect, the more information you get. Is it possible, is it even feasible to build a telescope with a mirror as big as that red circle? 100 meters in diameter. Well, in principle, it's possible to build one. Part of the problem is it's really expensive, and the expense really goes up as you go to larger and larger telescopes. But the second problem is, what would you call it? We've already had the very large telescope. We are now in the process of building and testing the extremely large telescope. So if you did ever build the telescope in red, 100 meters in diameter, if you ever got the money to do it, what would you call it? Somebody has suggested the owl. Is that because owls have large eyes? No, it's because it would be the overwhelmingly large telescope. The bottom line is, we need survey telescopes to survey the night sky and, over a period of time, tell us what is up there. Rather than just assuming that we think we know, let's survey everything that we can see down to a certain brightness, a certain faintness, if you like. Let's have a look at all the galaxies we can count. Tens of billions of galaxies. Let's count them and classify them and catalog them so we know what's out there. And let's do the same with stars, and let's do the same with asteroids and comets and all the objects in the solar system. We need survey telescopes to tell us what's out there. And then we need to tell large aperture telescopes, like the extremely large telescope, go look at this object, it looks interesting. Go look in more detail, collect the light from this faint object, see what you can learn about this distant object, this distant galaxy. And we need space telescopes to get above the blurring effects of the Earth's atmosphere to, again, get the sharpest possible images of various distant objects which have been found by the survey telescopes. So with all of these telescopes working together, complementing each other, surveys to tell us what's out there, large aperture and space telescopes to go look in detail, hopefully in years to come we'll be able to answer a lot of the questions that we're now asking about the universe. But even more importantly, it'll tell us which questions we haven't even asked yet. Thank you all for listening.